3 storms, 10 days, 21 states, 7 million people already in the danger zone, and the first one has not even arrived yet. What the forecast models locked onto overnight is not a bad week of spring weather. It is a sequential atmospheric detonation, 3 separate systems firing down the same corridor before the ground has time to dry, before the power comes back on, before anyone has recovered from the round before. Tornadoes, winds pushing 80 miles per hour across entire regions at once. Flooding that could hit the same counties twice. And when the last storm finally clears, the models agree on something that almost nobody is talking about yet. A temperature crash so steep it could swing 60 to 80 degrees in a single week. Stay until the end, because this is 2026's first major outbreak and it is just getting started. If this has you hooked, subscribe to the Skylab, where we are tracking this in real time. You do not want to miss what comes next. Also, drop a comment telling me where you are watching from and your honest opinion on whether you think 7 million people are truly prepared for what the atmosphere is about to deliver. Now let's get into it. Something changed in the last 24 hours. And if you live anywhere between Texas and Pennsylvania, you need to know what it is. 3 storm systems, back to back, lining up across the interior of the United States like freight trains on the same track. We are not talking about a rough week of weather. We are talking about a sequential outbreak pattern, a rare atmospheric setup where the same corridor of the country gets hammered not once, not twice, but 3 separate times inside 10 days. 21 states are sitting inside the potential severe weather footprint right now. Over 7 million people are already flagged inside an enhanced risk zone by the Storm Prediction Center, and the window opens on March 6th. Here is what made forecasters stop and pay attention. For several days, the 2 most powerful weather prediction tools on the planet, the European model, known as the ECMWF, and the American model, known as the GFS, were telling 2 different stories. That kind of disagreement is normal in early forecasting. Chaos rules the atmosphere at long range, and the models know it. But then, in the last 24 hours, those 2 models snapped into agreement. Same corridor, same timing, same 3-wave structure. And when independent global models converge like that, it usually means one thing. The large-scale atmospheric forcing has grown so dominant that the small-scale chaos no longer matters. The pattern is locked in. Think of it this way. Imagine 2 different detectives working the same case separately, with no communication between them. For days, they reach different conclusions. Then one morning, they both walk into the office and hand in the same report. That is when you know the evidence has become undeniable. That is exactly what happened in the forecast models overnight. What the models are describing is something meteorologists call a conveyor belt pattern. A large trough, a dip in the jet stream, has locked itself into place over the western United States. And like a wheel spinning in one direction, it keeps rotating disturbances off its eastern edge, one after another, sending them northeast along the same track. Each disturbance pulls warm, moist air up from the Gulf of Mexico. Each one has the wind shear and instability to fire severe thunderstorms. And because the trough stays parked, there is no reset. The atmosphere reloads between waves and then fires again. The Storm Prediction Center issued a Day 7 severe weather probability area for this sequence, something they reserve for events where confidence is already unusually high at long range. That is not a routine move. That is a forecasting organization telling you they have seen enough. And the fact that we are doing this in early March, traditionally the ramp-up phase of tornado season, rather than its peak, is what separates this pattern from anything we have seen so far in 2026. The next 10 days could produce repeated rounds of tornadoes, catastrophic winds, and dangerous flooding across the same communities before any of them have time to recover. And if you think Wave 1 is the dangerous part, wait until you hear what Wave 2 is expected to do at night. There is a specific corridor in the United States that the atmosphere has essentially targeted right now. It runs from the Texas Panhandle northeast through Oklahoma, Kansas, Missouri, Illinois, Indiana, Ohio, and into Pennsylvania. If you trace that line on a map, it looks almost too clean, like someone drew it with a ruler. But that line is not random. It sits directly beneath the intersection of two forces that have shaped North American weather for millions of years. The first force is Gulf moisture transport. The Gulf of Mexico acts as an enormous heat engine and moisture reservoir. When the right pressure pattern sets up, it pulls warm, humid air off the Gulf surface and funnels it northward across the plains and into the Midwest. That moisture is fuel. It loads the lower atmosphere with energy that, when released, powers thunderstorms capable of generating tornadoes, damaging hail, and extreme winds. The second force is the mid-latitude storm track, the highway that disturbances travel along as they move from west to east across North America. When that storm track lines up directly over the Gulf moisture plume, you get severe weather. When it locks into place and refuses to shift, you get repeated severe weather across the same region. That is what is happening right now. The current large-scale setup over North America is what meteorologists call a ridge west, trough east configuration, though right now it is more accurately a locked trough in the west. The western trough acts like a storm generator. It spins up low-pressure systems continuously, one after another. Each low tracks northeast. Each one deepens as it ingests warm Gulf air. Each one has the dynamics aloft, the jet stream winds, to support supercell thunderstorms and squall lines. And because the trough is parked, each storm follows nearly the same track. This is the phenomenon of storm track recycling. It is not common. Most severe weather patterns fire once, exhaust themselves, and allow the atmosphere to stabilize before the next event. But every so often, the large-scale pattern locks in so firmly that multiple disturbances follow the same atmospheric lane within days of each other. The communities along that lane do not get a break between events. They experience what cascades into a sequential disaster situation, where the power is still out from the first storm when the second one arrives, where rivers swollen from the first round of rain face a second round of rainfall on top. Historical outbreaks during highly active spring patterns show exactly this dynamic playing out. The same counties hit in one wave find themselves under tornado watches again 48 to 72 hours later. The same emergency management teams are still running operations from the first event when the sirens go off again. There are historical examples across the plains and Midwest where communities in this exact corridor faced multi-day, multi-wave sequences during years with strong seasonal transitions. And this is the critical point of the entire pattern. These are not isolated weather events. They are a cascade. And if the models are right, this corridor is about to experience that cascade in real time, starting in less than 48 hours. So what is it about early March that makes this setup so unusual and arguably more dangerous than the same pattern in May? Early March is not supposed to work like this. That is not an opinion. It is a statistical fact about how the atmosphere normally behaves this time of year. The typical March severe weather day is a localized affair. A single supercell fires over the southern plains. Maybe a brief tornado touches down. The event ends in a few hours and the atmosphere settles back into a winter-like pattern. Multi-state, multi-wave outbreak sequences are the territory of late April, May, and early June, not the first week of March. The reason for that is the seasonal energy budget. Severe weather requires three ingredients to produce the most dangerous outcomes: moisture, instability, and wind shear. In early March, you almost always have the wind shear. The jet stream is still strong, roaring along at high speeds, driving powerful dynamics aloft. What you typically lack is the moisture and the instability. The Gulf of Mexico has not yet warmed enough to pump serious humidity northward. The land surface has not absorbed enough solar energy to generate the steep temperature gradients that CAP, convective available potential energy, needs to reach dangerous levels. CAPE is the critical number. It measures how much energy is available in the atmosphere to accelerate air upward into a thunderstorm. Think of it as compressed spring energy stored in the lower atmosphere. The warmer and more humid the air near the surface, the higher the CAPE. The colder and drier the air aloft, the more violently that stored energy gets released when a storm tap releases it. High CAPE environments are the ones that produce the storms capable of generating tornadoes that stay on the ground for miles. This setup has something that early March almost never delivers: temperature departures of 20 to 40 degrees Fahrenheit above normal across large portions of the eastern United States. That is not a nuance. That is an anomaly. Temperatures running 20 to 40 degrees above where they should be this time of year mean the atmosphere is carrying energy levels more consistent with late April or May. The moisture return from the Gulf, which should be modest and inconsistent this early in the year, is instead running robust and continuous. And because the jet stream is still in its winter configuration, strong, fast, and packed with wind shear, you end up with the worst possible combination: spring-level energy inside a winter-strength dynamic environment. Meteorological history is full of catastrophic tornado outbreaks that occurred during exactly these seasonal transition windows. Some of the deadliest tornado events on record in the United States happen not in the statistical peak of tornado season, but in March and April, when winter dynamics and spring moisture collided under the right large-scale pattern. The atmosphere does not check the calendar, it responds to physics. And right now, the physics of this pattern are aligned in a way that forecasters rarely see this early in the year. Every ingredient arrived unusually early and unusually strong. Which brings us to the first sign that something was already happening. 3 days ago, the atmosphere gave us a preview. The sequence actually started on March 3rd. A precursor storm system moved through the same atmospheric corridor that is now being targeted by the three-wave outbreak ahead. Ice storms hit parts of the Appalachians. Over 1,000 schools closed across Pennsylvania, Virginia, and surrounding states. Severe hail reports came in from cities like Indianapolis and Springfield. Forecasters, watching the larger pattern developing behind it, described that storm as the appetizer. That framing matters. The March 3rd system was not a random event. It moved along the same corridor, fed by the same moisture transport, driven by the same trough-west setup. It was the first disturbance to rotate off the western trough before the larger sequence began. And its impacts, the ice, the hail, the school closures, were a sign that the atmosphere was already charged and primed even before the major waves arrived. The stored energy was already building. The corridor was already active. Wave 1, arriving around March 6th, does not mark the beginning of atmospheric instability in this region. It marks the moment that instability reaches full power. Wave 1 ignites along one of the most reliable storm initiation boundaries in North America. The dry line is not a metaphor. It is a physical line in the atmosphere, a boundary where hot, dry desert air flowing east off the Rockies and southwestern plateaus collides with warm, moist air flowing north off the Gulf of Mexico. On one side of that line, the air is 40 to 50% relative humidity. On the other side, it is 70 to 80%. Walk across a dry line and you can feel it. The air changes. That contrast is not just a curiosity, it is one of the most powerful storm initiation mechanisms on the planet. Dry lines work because the contrast in air density on either side creates a lifting mechanism. Warm, moist air is forced upward along the boundary. When the atmosphere above is unstable, when the upper air is cold enough relative to that warm surface air, storms explode along that line with remarkable speed. And this particular dry line setup is not subtle. Strong wind shear is already present thanks to the active jet stream overhead. Gulf moisture is abundant. The Cape values forecast for this event are well above seasonal norms. The geographic focus is the Texas Panhandle, western Oklahoma, and southern Kansas, with major cities like Amarillo, Oklahoma City, and Wichita sitting close to the initiation zone. What happens along a dry line like this, in conditions like these, is the formation of isolated supercells. A supercell is not just a big thunderstorm, it is a thunderstorm with a persistent rotating updraft, a structure called a mesocyclone that gives it the ability to sustain itself for hours and travel hundreds of miles. Supercells are the primary producers of large tornadoes, hail the size of baseballs and grapefruits, and the kind of intense downdrafts that can throw a car off a road. The late afternoon heating cycle on March 6th will act as the final trigger. As the sun heats the ground through the afternoon, temperatures spike, Cape increases, and the dry line surges eastward. Storms fire, and this is not the main event. This is Wave 1, the ignition point of a sequence that grows more dangerous with each chapter. But here is the thing about dry line storms that makes them simultaneously compelling and dangerous to forecast. They do not always behave the way the setup suggests they should. The Storm Prediction Center has placed a 5% hatch tornado probability area over the Texas Panhandle and western Oklahoma for the Wave 1 period. To anyone who has not spent time reading severe weather outlooks, 5% sounds modest. It is not. That number is a coverage probability. It is the likelihood that a tornado will occur within 25 miles of any given point inside the outlined area. 5% hatched means that if tornadoes do form, they are expected to be significant. EF, 2 or stronger. That is the kind of tornado that removes roofs, destroys well-constructed homes, and kills people who did not find adequate shelter in time. The distinction between coverage probability and intensity probability is one of the most misunderstood aspects of severe weather forecasting. A broad 10% tornado probability does not mean a large outbreak is guaranteed, and a narrow 5% hatched probability does not mean the risk is low. It means the coverage is limited, but the potential for severe individual tornadoes is elevated. Many of the most devastating tornado events in American history began under relatively modest coverage probabilities paired with high-intensity indicators. The atmosphere does not need to produce 50 tornadoes to be catastrophic. One long-track EF4 crossing a populated corridor can cause more fatalities and damage than 30 brief touchdowns in empty fields. What makes the Wave 1 tornado environment particularly unstable is the combination of factors driving storm rotation. Wind shear in this context means the change in wind speed and direction with height. Near the surface, southerly winds feed warm moisture northward. At mid-levels, winds shift to the southwest. At upper levels, the jet stream rips along from the west or northwest at high speeds. That directional and speed change with altitude puts a spin into thunderstorm updrafts. When a storm's updraft is strong enough and the shear is deep enough, that spin tightens into a mesocyclone. And under the right thermodynamic conditions, that mesocyclone can lower a rotating wall cloud toward the surface and produce a tornado. Forecasting exactly when and where that process will occur remains one of the hardest problems in meteorology. Storms with nearly identical environmental profiles sometimes produce powerful tornadoes and sometimes do not. Small-scale variations in moisture, in the exact position of the dry line, in the timing of upper-level forcing, all of these can shift the outcome. That inherent uncertainty is precisely why forecasters watch these events in real time, adjusting outlooks as storms evolve. But even at this range, the setup for Wave 1 is clear enough that ignoring it would be a mistake. Even a small number of strong tornadoes moving through the populated corridor between Amarillo and Oklahoma City can produce major human consequences. And the tornado threat is not even the full story of what Wave 1 is likely to do as it evolves. Severe weather outbreaks follow a predictable life cycle, and understanding that cycle matters because the hazard profile changes completely from beginning to end. It starts with isolated supercells forming along the dry line during the afternoon heating cycle. These are the tornado-capable storms, discrete and rotating, each one an autonomous severe weather engine tracking northeast. They are dangerous, but geographically focused. A supercell's damage swath might be a few miles wide and a few dozen miles long. Deadly, but contained. As the afternoon gives way to evening, something changes. The low-pressure system deepens. More energy arrives from aloft. The storms begin to interact with each other, their outflow boundaries colliding and merging. Discrete supercells cluster together, and when storm clusters reach a critical density and the upper-level wind pattern organizes them, they stop behaving like individual storms and begin behaving like a single enormous system. They form what meteorologists call a squall line, a wall of thunderstorms stretching hundreds of miles across multiple states, advancing like a front. Inside a squall line, the tornado risk largely transitions to a wind threat. The rotating updrafts that produce tornadoes are disrupted by the storm merger process. But what replaces them is in some ways more broadly destructive. Squall lines produce bow echoes, sections of the line that bulge forward like a breaking wave. And inside those bow echoes, straight-line winds can reach 70, 80, even 90 miles per hour. Wind fields that wide do not damage a single county. They damage a corridor several states long simultaneously. Power lines go down across entire regions. Highways become dangerous with downed trees. The infrastructure impacts of a major wind event often exceed those of the tornadoes that preceded it, simply because of the geographic scale. Wind damage from severe squall lines accounts for more total economic losses in the United States than tornadoes do in most years, precisely because the affected area is so much larger. And this transition from discrete supercells with a tornado threat to an organized squall line with a regional wind threat is the typical arc of Wave 1. It begins as an ignition event and ends as a regional impact event. But here is what makes this pattern truly unlike a typical severe weather outbreak. Once Wave 1 ends, the atmosphere doesn't stabilize, because the western trough that generated it is still there, still spinning, already loading the next disturbance. Under almost any other large-scale pattern, a severe weather outbreak like Wave 1 would be followed by atmospheric stabilization. A cold front sweeps through. Drier, cooler air floods in behind the storms. The Gulf moisture gets cut off. Cape values crash, the jet stream shifts position. The atmosphere essentially exhales and resets, and severe weather forecasters get a few days to breathe before the next setup begins to develop. That is not what happens here, because the western trough is not moving, it is locked. And locked troughs do something that makes meteorologists deeply uncomfortable. They manufacture disturbances in series. These disturbances, shortwave troughs, energy packets embedded in the flow, rotate around the base of the larger trough and eject northeast one after another. Each shortwave is essentially a trigger mechanism. It provides the upper-level lift needed to fire convection. It deepens surface low pressure. It organizes the wind shear that produces rotating storms. And because the Gulf moisture stream remains active, because the warm, humid air at low levels is continuously being fed northward by the pressure pattern, each new shortwave arrives in an atmosphere that has already partially recharged. Forecast models are showing another significant disturbance arriving within 24 to 48 hours of Wave 1's departure. The atmosphere barely exhales before it inhales again. The cape that was consumed by Wave 1's storms begins to rebuild. The moisture that was partially wrung out by Wave 1's rainfall is partially replenished. And when the next shortwave arrives as the trigger, it finds an environment that, while not quite as energetic as before the first round, is still more than capable of producing severe weather. Meteorologists have a phrase for this: a storm conveyor belt. And it describes exactly what this pattern has become. The critical implication is this: Wave 1 is not the outbreak. Wave 1 is the opening act. The three-storm sequence is the structure the atmosphere has locked in. And Wave 2, arriving right behind it, is the one that forecasters are watching with the most concern. Wave 2 is different from Wave 1 in almost every way that matters. It is larger. It is more energetic. It arrives into an atmospheric corridor that has already been partially primed by the first storm, and it targets a population corridor significantly denser than the dryline initiation zone of Wave 1. The Storm Prediction Center's enhanced risk zone for Wave 2 is centered over eastern Kansas, eastern Oklahoma, and western Missouri. That bullseye sits directly over or near Kansas City, Tulsa, and Wichita. These are not small cities in isolated plains counties. These are major metropolitan areas with millions of residents spread across urban and suburban environments where tornado sheltering, particularly in apartment complexes, mobile homes, and older construction, can be deeply inadequate. The difference between a tornado crossing an agricultural field and a tornado crossing a densely populated suburb is not meteorological. It is entirely about what is in the path. Ahead of Wave 2, the warm Gulf moisture that has been feeding northward continuously deepens significantly. The boundary layer, the lower atmosphere where energy is stored, loads up with humidity values far above early March norms. Cape values forecast for this event are substantially higher than Wave 1. The wind shear environment is favourable for supercell development. Forecast models show storms initiating as isolated supercells before the system organises, which means the tornado-producing phase of Wave 2 could be more robust than Wave 1 before the inevitable squall line merger occurs. The conditional risk area, the broader zone where any severe weather at all is likely, stretches from Dallas all the way to Chicago for this event. That is not a forecast uncertainty box. That is the actual geographic footprint of potential hazards. Tornadoes, large hail, and damaging winds could occur anywhere along that corridor. But the enhanced risk zone is where the atmospheric physics are most hostile, and that is where the most significant events are expected to concentrate. This wave has the structure of a classic major outbreak. The ingredients, the timing, the geographic focus, the population exposure, it all lines up in a way that Wave 1 does not quite match. If any single event in this 10-day sequence produces the most dramatic impacts, Wave 2 is the overwhelming favourite. But Wave 2 has one more dimension that Wave 1 largely lacks. The most dangerous phase of Wave 2 is not the afternoon supercell phase. It is what happens after dark. Tornadoes at night are fundamentally different from tornadoes in daylight, not in terms of the atmospheric physics that produce them, but in terms of human survivability. During the day, a visible tornado gives people time to react. Storm chasers post video in real time. Residents can look outside and see rotation descending from the clouds. Emergency managers watch radar and coordinate warnings before storms arrive, but at night the visual cues disappear. A tornado crossing open countryside at 11 p.m. is invisible. It is a sound, a roar that by the time it registers means the tornado is already there. People who are asleep do not hear wireless emergency alerts. People in apartments or mobile homes may receive a warning but have nowhere adequate to shelter. The historical statistics on nocturnal tornadoes are sobering. Studies of major tornado outbreaks show that events occurring primarily at night produce significantly higher fatality rates per tornado than identical events occurring during daylight hours. The Joplin tornado of May 22, 2011 struck at early evening, still light enough for many residents to see it coming. Outbreaks that struck in the early morning hours between midnight and 4 a.m. produced some of the highest per capita casualty rates in tornado history, precisely because the warning to shelter time was effectively zero for sleeping populations. Forecast models show Wave 2 storm activity continuing into the overnight hours across Texas, Oklahoma, Arkansas, and Missouri. Supercells embedded within the developing squall line, which can still produce tornadoes even as the broader storm system shifts toward a wind event, will be moving through populated areas during the hours when the vast majority of residents are asleep. Radar interpretation at night becomes more challenging. The visual confirmation that meteorologists and chasers rely on during daylight is absent, and the storm system is still moving. Still rotating, still capable of producing tornadoes even after the prime afternoon tornado window has passed. This overnight window is not a footnote to the Wave 2 threat. It may be the most consequential phase of the entire outbreak. And while tornadoes at night represent one layer of the hazard, the storm sequence has been building a second threat that works on a completely different timescale. By the time the overnight hours arrive across the central United States during Wave 2, the atmospheric situation transforms from a collection of individual severe thunderstorms into something more like a weather system with the dimensions of a small country. The squall line that began consolidating during the evening hours over eastern Kansas and Oklahoma continues to grow. Its leading edge expands north and south simultaneously. Its winds, organized by the bow echo structure at its core, push ahead of the line like a pressure wave. The forecast timing for this squall line's progression places it over Kansas City around 10 p.m. It reaches Chicago around 2 a.m. The Ohio Valley sees it by morning. That progression covers roughly 700 miles of distance in approximately 8 hours. An average forward speed of nearly 90 miles per hour for the system, though the damaging winds within it can briefly exceed that. In practical terms, every community along that corridor has perhaps 30 to 45 minutes of warning time between the moment sirens go off and the moment the line arrives. Bow echoes, the curved, bulging sections of squall lines associated with the most extreme straight-line winds, work by a process of rear inflow. Cold, dry air gets drawn in from behind the squall line, descends rapidly, and accelerates forward toward the leading edge of the storms. When that rear inflow jet is strong enough, it can produce straight-line winds that exceed 70 or 80 miles per hour across an area spanning hundreds of miles simultaneously. These are not localized gusts. These are sustained, damaging winds moving through entire metropolitan areas, snapping power poles, flattening roofs, toppling semi-trucks on interstate highways. The term derecho describes a particularly intense form of this wind event, a long-lived, widespread convective windstorm that can travel over 1,000 miles while maintaining severe wind gusts the entire way. Not every squall line becomes a derecho, but the setup for Wave 2 has characteristics that historically produce that kind of organization. And if that happens, the power outage footprint across the Ohio Valley and Great Lakes region could rival the impact of a landfalling tropical storm in terms of sheer square mileage affected. But straight-line winds are not the only way Wave 2 threatens lives and infrastructure across this region, because underneath these storms, the ground is quietly running out of places to put the water. The rainfall associated with Wave 2 is not incidental, it is structural. The same atmospheric setup that produces the severe thunderstorms, the deep moisture, the persistent Gulf moisture transport, the slow-moving frontal boundary, also produces extreme rainfall totals. Forecast models are projecting 4 to 10 inches of rainfall across parts of the Southern Plains and Midwest in the Wave 2 window, with localized totals potentially higher in areas where training storms develop. Training storms are a specific and particularly dangerous rainfall phenomenon. They occur when a series of individual storm cells forms along the same boundary and moves in the same direction as the storm motion, like boxcars on a train passing over the same section of track one after another. Instead of a single storm dropping 2 inches of rain over a county in 30 minutes, you get 5 successive storms each dropping 2 inches, all over the same county in the span of a few hours. The ground, the creek beds, the storm drains, none of them can absorb or redirect that volume of water in real time. Flooding begins. And it does not stop when the last storm passes, because the runoff from saturated soils continues feeding creeks and rivers for hours after the rain ends. The regions at highest risk for this scenario include southeast Oklahoma, northeast Texas, and western Arkansas. These areas sit in the moisture convergence zone, where the Gulf feed is strongest and where the frontal boundary is expected to stall or slow, allowing repeated rounds of heavy rainfall over the same terrain. Some of these areas have experienced drought conditions in recent months, which paradoxically increases the short-term flood risk. Hardened, drought-compacted soils shed water rather than absorbing it, routing runoff immediately into drainage systems already overwhelmed by the rainfall rate. Flooding kills more Americans in severe weather events than tornadoes do in most years. Not because individual flood events are more violent, but because floods are broader, slower developing in terms of public perception, and frequently encountered by people who make the critical mistake of attempting to drive through water-covering roadways. The combination of severe thunderstorms and catastrophic flooding in the same event window creates exactly the kind of multi-hazard environment that stretches emergency management resources to their limit. And this is not a single event. It is the middle wave of 3, which is why what happens at day 7 may be the most important signal of all. While Wave 2 is still being tracked hour by hour across the plains and Midwest, forecast models are already showing the third disturbance rotating off the Western Trough. Wave 3 is expected to arrive somewhere in the March 9th to 11th window, and the Storm Prediction Center has done something that almost never happens at that lead time. They issued a 15% severe weather probability area 7 days in advance. A 15% severe weather probability sounds less alarming than it is. This means that within the outlined area, there is a 15% chance that at least one severe weather event will occur within 25 miles of any given point. At day 7 of a forecast cycle, that is extraordinary. Long-range severe weather outlooks issued 5 to 7 days before the event, are typically reserved for situations where large-scale atmospheric forcing is so dominant that even at extended range, the models cannot wriggle free of the signal. The ECMWF and the GFS are both showing storm redevelopment. Same corridor, same regions. Texas, Oklahoma, Missouri, Arkansas, Illinois, the same states that Wave 1 and Wave 2 will have already hit. The atmosphere essentially reloads between waves. The Gulf moisture feed continues. The Western Trough remains anchored. The shortwave disturbance rotating around its base arrives with enough energy to once again lift the rebuilt instability into severe thunderstorms. In a typical outbreak pattern, the third storm in a sequence is the weakest. The atmosphere has been partially stabilized by the preceding events, and the energy supply has been partially exhausted. But this pattern is not typical. The continuous Gulf moisture transport means the energy supply is not being exhausted. It is being continuously replenished. Wave 3 confirms what the model agreement has been suggesting since the pattern locked in. This is not three separate weather events that happen to occur close together. This is a single, multi-system outbreak pattern operating as one atmospheric sequence. The 10-day window from March 6th to roughly March 11th represents a continuous period of severe weather risk across the same corridor, with brief reloading intervals between waves that offer little actual relief. And Wave 3 carries with it a set of hazards that are different from what Wave 1 and Wave 2 will have produced. The three-wave structure of this outbreak comes down to a single atmospheric mechanism, and understanding it changes how you see the entire event. The Western Trough, that persistent dip in the jet stream parked over the Rockies and Great Basin, is not just a storm track. It is an energy recycling system. Here is how it works. Before any storm fires, the lower atmosphere fills with warm, humid Gulf air. That air carries potential energy stored in the temperature and moisture contrast between the surface and the air aloft. When a shortwave disturbance arrives from the west, it provides the lift needed to release that energy. Thunderstorms form. The energy discharges. The storm produces tornadoes, hail, and wind. It dumps rain. The process feels violent precisely because it is the rapid release of stored atmospheric potential. After the storm passes, the energy in that column of air has been depleted, but the trough keeps spinning. And between disturbances, the Gulf moisture feed does not shut off. Warm, humid air continues pushing northward from the Gulf, refilling the lower atmosphere. Surface temperatures, still anomalously warm, continue generating instability from below. The upper atmosphere cools back down. Gradually, over 24 to 48 hours, the atmospheric column recharges. The potential energy rebuilds. And when the next shortwave arrives, it finds a recharged atmosphere ready to discharge again. Compare it to waves hitting a shoreline. Each wave expends its energy crashing against the beach and then pulls back. The next wave builds offshore and arrives. The shoreline, the corridor from Texas to Pennsylvania in this case, does not get to recover fully between impacts. It gets hit, pulled back, and hit again. Over the course of 3 waves in 10 days, the accumulated impacts compound. Infrastructure stressed by Wave 1 faces Wave 2. Emergency resources stretched by the second round face the third. And throughout this entire sequence, a secondary process has been building in the background, one that will fundamentally change the entire atmospheric setup within days of the final storm's passage. Wave 3 carries a complication that neither Wave 1 nor Wave 2 fully delivers: the possibility of multiple weather types occurring simultaneously within the same system. As the third disturbance drives a cold front through the corridor, the temperature gradient behind that front, the contrast between the warm, Gulf-fed air being swept eastward and the colder air advancing from the northwest, becomes intense enough to support a range of precipitation types across different elevations and latitudes simultaneously. Severe thunderstorms could be occurring along the southern portion of the system's leading edge, while the northern flank produces heavy snow. In the Appalachian Highlands, West Virginia, southwestern Pennsylvania, parts of western Virginia, the rapid temperature fall following Wave 3's passage could transition active rainfall directly into snow within a matter of hours. Strong temperature gradients like this do not appear in a quiet, slowly evolving atmosphere. They appear in highly dynamic systems where large air masses with very different thermal properties are being forced together by powerful upper-level winds. That kind of rapid thermal contrast within a single system is also a diagnostic signal about the larger pattern. The atmosphere has accumulated an enormous temperature imbalance over the past several weeks. Anomalously warm air has built across the south and east, while cold air has been displaced into the north. The 3-storm sequence is, in one sense, the atmosphere's attempt to correct that imbalance. Warm air gets lifted, mixed, and displaced. Cold air advances behind the fronts, but the correction in this case is not going to be gradual. And some forecast models suggest what happens after Wave 3 is less of a gradual seasonal adjustment and more of a violent atmospheric overcorrection. Somewhere out ahead of all of this, deployed across open plains under threatening skies, storm chasers are already beginning to position their vehicles for the week ahead. The outbreak beginning March 6th will bring a significant deployment of storm chaser teams across the southern plains and Midwest. Tornado-producing supercells in accessible terrain draw professional and amateur chasers in large numbers, and this pattern, 3 waves of severe weather across open plains terrain, is exactly the kind of sequence that fills the plains with vehicles bristling with cameras and sensors. Modern storm chasing combines scientific observation with real-time media in ways that fundamentally change how the public experiences severe weather events. Live streams broadcast from moving vehicles directly inside storm environments reach hundreds of thousands of simultaneous viewers during major tornado events. Drone footage, forward-facing cameras, and mobile radar units provide documentation of storm structure and tornado behavior that would have been impossible to capture 15 years ago. That footage, when a significant tornado occurs, can go globally viral within minutes. The scientific value of chaser data is real. Mobile Mesonet vehicles gather temperature, humidity, and pressure measurements that help verify and improve forecast models. But the social media amplification of chaser footage during a 3-wave outbreak across the same corridor will also serve as a running visual record of just how unusual it is to watch the same states absorb multiple outbreak-level events inside a single week. That visual record will reinforce for millions of viewers watching in real time exactly what the models have been showing for days. This is not a typical severe weather week. And the story does not end when Wave 3 clears the East Coast. Around March 14th, the atmospheric configuration that has driven everything, the 3 waves, the Gulf moisture stream, the severe weather corridor, the warm temperature anomalies, begins to undergo a fundamental reversal. The jet stream pattern shifts from a configuration that has been pumping warm air northward to one that opens the door for cold Arctic air to pour southward from Canada. Meteorologists describe this as a ridge-west, trough-east flip. In the previous pattern, the ridge, the high-pressure dome, sat over the east, holding cold air at bay while warm air circulated northward. In the flipped pattern, that ridge shifts west and the trough migrates east, pulling cold polar air down into the central and eastern United States along the same geographic corridors that just experienced severe weather. The warm air that fueled 3 storm outbreaks does not simply dissipate. It gets displaced, forced east and eventually out to sea as a cold air mass of significant depth advances from the north. The magnitude of this forecast cold surge is what separates it from a routine pattern change. Some models show temperatures dropping below seasonal norms across large portions of the central and eastern United States in the days following Wave 3. The warmth that was running 20 to 40 degrees above normal, the warmth that loaded the atmosphere with enough energy to fire a multi-wave severe weather outbreak in early March, gets replaced by cold air that, in some scenarios, falls below seasonal norms by comparable margins. The atmosphere is attempting to rebalance the temperature debt it accumulated over the previous weeks, and it is doing so rapidly and dramatically. This is the same pattern that generated the 3 storms now finishing its work, the warm air spending itself, the balance reasserting itself. But the scale of the temperature swing that follows is going to be unlike anything this region has experienced in a long time. The forecast temperature swings being modelled for mid-March are difficult to process in abstract terms, so consider them concretely. Some regions of the central United States that will be experiencing temperatures in the 70 to 80 degree Fahrenheit range during the Wave 2 and Wave 3 severe weather events could be approaching near freezing temperatures within the same calendar week. That is a potential temperature swing of 60 to 80 degrees Fahrenheit occurring over 5 to 7 days in a single week, on the same streets where tornado warnings were active days before. The physical mechanism driving temperature swings of that magnitude is the concept of baroclinicity, the degree to which temperature differences over a geographic area drive atmospheric circulation. In a highly baroclinic atmosphere, the contrast between warm and cold air masses is large, and that contrast generates the strong jet stream winds and intense low-pressure systems responsible for severe weather. The storms themselves are a product of baroclinicity, but baroclinicity also drives the cold fronts that follow the storms. The steeper the temperature gradient, the faster and more intense the cold air advance. It is worth being precise about the uncertainty here. The European model, generally regarded as the more reliable of the two major global models for medium-range forecasting, is currently showing a more aggressive cold surge than the American GFS model. Model disagreement at 2 weeks range is normal and expected, but the direction of disagreement, both models showing substantial cold, with one showing it more dramatically, is itself a signal. The cold flip is not a fringe scenario, it is the central forecast. Its exact magnitude remains uncertain, but the pattern change itself appears locked in. The three-storm outbreak is, in a very real sense, the mechanism through which the atmosphere releases the temperature imbalance that has been building. The storms are the process. The Arctic air behind them is the result. And for some regions, that result is going to arrive with remarkable speed. Some forecast models indicate a transition that would be nearly incomprehensible to experience firsthand. Regions currently sitting under severe thunderstorm watches, where tornado sirens may have activated hours or days before, could experience active snowfall within the same 24 to 48-hour window as Wave 3 clears the region. The higher elevations of the Appalachians, including parts of West Virginia and southwestern Pennsylvania, are the most likely candidates for this kind of rapid transition. The mechanism is straightforward, even if the experience of it is not. When a strong cold front sweeps through quickly behind an active weather system, surface temperatures can drop 15 to 20 degrees Fahrenheit in a matter of hours. If the atmospheric column above is already saturated with moisture from the preceding storm activity, and if the temperature drop is rapid enough to push that moisture below freezing before it can precipitate out, the transition from rain to snow can happen with almost no gradual intermediate phase. 1 hour it is raining heavily, 2 hours later it is snowing. 3 hours after that, it may be accumulating. These rapid transitions are not common outside of highly dynamic storm systems, and they do not happen in slowly evolving spring patterns. They require exactly the kind of extreme thermal contrasts that exist right now. Contrasts that are a direct product of the same atmospheric imbalance driving the three-storm sequence. The warm air and cold air are not drifting gradually past each other, they are colliding. And along the collision zones, the weather can shift from one season to another in the time it takes to drive across a county. There is a question sitting behind all of this that the meteorological community has been wrestling with for years, and a 10-day outbreak sequence in early March is exactly the kind of event that puts it back in focus. Scientists who study the behavior of the atmosphere over long time periods continue to examine whether patterns like this one, multi-wave outbreak sequences that arrive unusually early in the season, driven by temperature anomalies that are 20 to 40 degrees above normal, followed by dramatic cold air crashes, are becoming more common. Some researchers point to evidence that stronger temperature gradients between warming tropical regions and still cold polar regions may be altering the stability of the jet stream, making locked patterns like the current one both more frequent and more persistent. Others emphasize that natural variability in seasonal transitions has always produced extremes, and that single events, no matter how dramatic, cannot be straightforwardly attributed to long-term trends. Both arguments contain truth, and neither provides certainty. The atmosphere is a system operating across timescales and spatial scales that challenge every simplification we apply to it. What can be said with confidence is this. The event unfolding right now is not statistically typical for early March. The ingredients, the anomalous warmth, the robust Gulf moisture feed, the locked trough pattern, the three-wave structure, the subsequent Arctic crash, all arrive simultaneously and with unusual intensity. Whether the future holds more events like this, or whether this is a rare expression of natural variability, remains an open question that will be informed by more data collected in part by the storms themselves. Here is the shape of what is about to happen. The atmosphere loaded up, it pulled warmth from the Gulf, banked energy in the lower atmosphere, and locked a pattern into place that forecasters almost never see this early in the year. Then, beginning March 6th, it begins to discharge that energy, not once but 3 times across the same corridor, against the same communities inside 10 days. Tornadoes, catastrophic winds, multi-inch rainfall and flash flooding, a squall line moving through the nation's interior at night while millions of people sleep. And then, when the third wave clears the east coast and the models flip, a temperature crash that erases the warmth almost as quickly as it arrived. The storms are only half the story. The real story is the cycle: warmth loading the atmosphere, storms releasing the energy, Arctic air resetting the system. It is the same cycle the atmosphere has run for as long as there has been an atmosphere. What makes the next 10 days unusual is not that the cycle is occurring. It is the scale at which it is occurring, the speed at which it is moving, and the fact that it is moving through 21 states in early March rather than May. Watch what happens. Because whether this turns out to be an extreme expression of natural variability or the opening signal of a historically active severe weather season, the atmosphere has made one thing unmistakably clear. It is not waiting. The pattern is locked, the energy is loaded, and the discharge begins now.